Right, good evening everybody. Thank you for being here. I thought it will be just one or two of you, but it's great to see a bit more numbers. As I mentioned in the email, I am trying to recording it. Hopefully everything will go fine, and then you'll be able to watch it again, and anybody who was not able to come will be able to see it as well. I don't know, the slides might not be visible enough in here, but I don't really want to turn anything off because then that would really influence the camera. So you all have the slides in front, so you should be able to cope, and the slides are up online anyway. So yeah, today we're going to do integration, and as always I'm going to take it nice and slow and talk to you about everything, and do ask your questions, because if you think about the questions, I can guarantee to you there is at least another person or two in the class who's thinking about the same questions that just doesn't really feel like daring to ask it. Okay, so hello, come in, slides there. Okay, so just briefly, I'm going to try to go through what is integration and what it is used for. Again, briefly mention what's the difference between indefinite and definite integrals. Then we're going to go into more details about the basic rules of integrations. Then we're going to mention the methods of integrations, because there is a difference in between those two. And going to look at infinite limits of integrals, a little bit of an economic applications, and at the very end of the lesson I'm going to lightly touch on double integrals, because when you start to introduce statistical functions and the marginal functions and the rest of it, you might need to be able to deal with double integrations. But double integrations is basically just the opposite of differentiating multivariate functions. So it's slightly backwards things, which kind of leads me on to the question: what is integration?
The opposite of differentiation.
Exactly. So in many cases, people do refer to them as antiderivatives. So you're doing backwards the differentiation. Now, what do you use the integrals for then?
Probability.
Probability. I can't hear that.
Probability.
Yes, you use them for probability and the rest of it in statistics. But in general, you use integrals if you were given a function and you said, okay, this is the derivative of a function, what was the original? Then you would use integration to go back and find the original function. Another very often used another topic of mathematics where integration is very often used is trying to find out areas under the curve or volumes and such sort of things. But that's not necessarily where you're going to use it as such. I mean the volumes, the area under the curve is something that you will use. So indefinite integrals, basically we're looking for the antiderivative. Now if I know that f prime of x is equal to small f of x, then the notation goes that integral of f of x dx will have to be equal to capital F of x. So that's just the notation that's going on, and you should be familiar with this. But there is a slight discrepancy there, because constant derivative is always 0. So therefore actually fx plus c derivative, doesn't matter what that c is, always going to be capital F prime of x. So when you do the integration and it's an indefinite integral, you always have to put a plus c on there. So actually you're not identifying a single function, you're identifying a family of functions. So basically when you do the indefinite integral, you identify an infinite number of functions, because there is infinite number of constants that you can add on to your capital F of x, and every single time whatever that constants would be, any of the infinite numbers would always end up being 0. So if you actually wanted to find the exact function that you started with, you need to know something called the initial conditions. I don't know if you went into those in details or not. That is sometimes used if you wanted to identify one particular function as the original of the derivative. don't worry too much about it if you don't need to know about it. Okay, so basically just the pictorial representation of what you're actually identifying at the end of the integration with that plus c. So the same function, but infinitely many times pushed up or down alongside the y-axis, because those are the plus c's when you're sort of moving it up and down. It's a slightly different function, it's probably a cubic, and again, it's all parallel, but pushed up or down infinitely many times. So this is what's going on at the background with that plus c. So that's what it means. Right, any questions? Right. Now, we also have something called the definite integrals. And for the definite integrals, we need to know something called the fundamental theorem of calculus. Then basically, if f is continuous on the closed interval ab, and capital F is the indefinite integral of f on the same interval, then integration between a and b, fx dx, you can just identify it as f at b minus f at a. So you identify the antiderivative of f, and you subtract the values of that specific function between the two ends of the intervals. That's relatively simple, but that also assumes that you already know how to find the antiderivative of specific functions. Okay? So graphically, the definite integral is the area under the curve. So this is, the green shaded area is basically what you find when you are identifying the integral over an interval. What happens if you end up with a negative number after the integration?
Number where?
So you've done the integral, you've done this integration, you plugged in capital F3 minus capital F5 or whatever, and the sum to that will be negative 2. What would that mean? Because I'm talking about area. So your first instinct would be, I can't really have, because area can't be negative.
So would it be the area above the curve instead?
No. That would mean that your curve would be down here. Okay, so that's when you end up with negative numbers. And that's in the notes. So I can tell you probably haven't looked at it in much details. I mean, by I mean notes, Arena's notes. Okay, not on mine. Yes, especially if you work and you have troubles like you mentioned at the beginning.
I'm sorry.
Yeah.
Again, because I haven't read her notes. If the curve is underneath.
Mm-hmm. If it's, so you are here.
Yeah.
And oops, you end up with a curve something like this, and you need to find the area in this interval.
But doesn't that area tell us the probability of getting?
Don't bring the probability in yet,
Okay,
because the probability is something totally different. Okay? What do you know about probability? What numbers, what values can any probability take?
0 to 1.
Exactly. So when it comes to probability, you will never find this. If you do, you've done something totally wrong. Because probability can't be negative, probability is only between 0 and 1. So this is generally talking about functions, any functions, but those functions that you use for probability are very specific functions. They have to fulfill some requirements before you can talk about that, okay, this is a probability function now. So they can't be any odd functions when you start to talk about probability. Okay, that's just the generals. Okay, so the basic rules of integration. Okay, and this is what you need to know by heart to be able to attempt any kind of integration problem. But thankfully, oops, those are very similar to the derivative rules. So you just have to sort of think backwards. Okay, so integral dx, what does that actually mean when I'm doing integral dx? The integral dx is basically integrating 1 according to dx. But what was the function which derivative gives you 1? X. So that's why the integral dx, because the one we usually don't write out. Mathematicians are lazy. So if you don't see numbers, that's usually referred to 1. So that will be x plus the c. Don't forget about the c, because it's again still just indefinite integrals. So integral k dx, and I should have made it clear that k is a real number. Okay, so what's the integral of that? It's basically just kx, plus c. Okay, because again, any function such as 3x, if you differentiate that, it becomes 3. So you're thinking backwards.
The funny e between the k and the r just means is, doesn't it?
Belongs to, is the element of.
That.
So it's a standard notation in set theory. K belongs to R. And this R should have double legs. And in this way, it means it's a real number, belongs to the set of the real numbers. Okay? So, now this rule might seem a little bit over the kill, but we need to think about what's going on in here. If you have got a power function, what do you do when you need to differentiate that? You bring the power down and you lower the power by 1. So when you do the opposite of that, you need to raise the power by 1, and you need to divide by that raised power. Otherwise, you won't end up with x to the n. You would end up with x to the n multiplied by another constant. So that's why you need to do it, to undo the differentiation effect of bringing the power down. Now, this is only if n is not equals to -1. Because f, well, you can use the n equals 0, because 0 plus 1 over 0 plus 1 just going to give you back the first rule. So that's fine. But it can't be equal to -1 because that is this rule. Because you know that the log's derivative is 1 over x. So 1 over x's integral have to be the log function. So integral 1 over x dx have to be equal to ln. Well, strictly speaking, in mathematics you should use these two lines in here. What do they actually mean when you put x in between these two parallel lines? Absolute value. What does an absolute value mean? Always positive. So positive number's absolute value is itself. Negative number's absolute value is the negative of that, which you make it positive. So basically it's the magnitude of the number. So absolute value of 3 is 3. Absolute value of -3 is also 3. So in a formal definition you can say, okay, what's the absolute value? The absolute value is the distance of a number from 0. So that's probably the easiest way to think about it, because distance is always positive. You can't have negative distance. You can't get closer than exactly the same point. And another one, e to the x was a funny one, because it was derivatives of itself. Therefore, the integral of e to the x will be e to the x again. So you have to know these rules. You more or less know them now because you learned the differentiation rules, but you just have to make sure that you're thinking backwards. Okay, so let's look at some examples. Okay, so tell me, what's the integral of this function?
3x.
Yes, exactly, 3x plus c. Second example.
ln x cubed?
Mm-mm. Because ln is only for 1 over x.
6x then minus 3 then.
Yeah.
So exactly, so I can bring this up and I can write this as 6 times x to the minus 3 dx. Okay, now here comes the trick, and I probably brought it in a little bit too early, this particular example and the previous one, another one along the line, because the 6 is a constant multiplier, and remember that we always kept that constant multiplier when it comes to differentiation. So you can bring the constant multiplier, nothing else, but the constant multiplier you can always bring outside in front of the integral sign. So I can rewrite this as 6 times integral x to the minus 3 dx, and from here on I can see that this is just a simple power rule. Okay, so it's a power of a function. Well, that power rule didn't tell me that I can't use it for negative numbers. It just told me I can't use it for negative 1. So any other negative powers is fine. So what I need to do now, keep the constant multiplier, x to the minus 3, add 1 to it, and minus 3 plus 1, and don't forget the plus c. So until you become familiar with all these calculations, and you can do them in one go, I suggest you write the rules out with the numbers and then deal with the algebra, and in that way it's a safer way. So that will be 6 times minus 3 plus 1 gives you minus 2 as in the power and also at the bottom of the fraction, plus c. 6 and minus 2 cancels down to negative 3. And if you wanted to write it in a proper mathematical way, you can always write it back 3 over x squared plus c. And that way it's probably the simplest and easiest form. And you can now see the kind of relationship, what's going on in there. As x increases, x squared will decrease. Sorry, the function overall value will decrease. Okay? Number 3, integral 4th root of x to the 5th dx.
X, 5 over 4.
Exactly, there is no rule for roots, simply because roots can be rewritten as powers, so we're again just going to use that power rule. So there's no constant multiplier. So what happens now? 5 over 4 plus 1 over 5 over 4 plus 1 plus c. So 5 over 4 plus 1, what is that going to be? 9 over 4, because 1 is 4 quarters, so you can rewrite that as 4 quarters, and 5 quarters add 4 quarters gives you 9 quarters. So x will be 9 quarters over 9 quarters. Now how do you divide by a fraction? Flip it around and multiply it, so you multiply by the reciprocal. So this is actually going to be 4 over 9 times x to the 9 over 4. Oops, I forgot the plus c, which is going to happen to you all the time as well. And again, if I wanted to be very precise mathematically, I'm now going to rewrite this as a root again. So it will be 4 over 9 times 4th root of x to the 9 plus c. And that's the final exact mathematical form. Now, whether I stop here or I stop here, that's absolutely my choice. I mean, not everybody writes back the root form all the time. There are people out there who prefer the fractional power to the root. It's your choice, or rather what your lecturer expects. But having said that, most mathematicians would totally accept both of them because they're absolutely identical. Okay, I'm gonna need more space. Is that all right if I rub the board off? Probably not the last one. By the way, if you get hot, please feel free to get up and open the windows because it seems to be quite warm in here. Or it's maybe just doing mathematics. So what can you see in this function? So what type of function is this? Yes, because x to the negative 1, that was the exception amongst the power functions. So basically I can bring the 5 out and I can rewrite this as 1 over x dx. And I need to remember that the 1 over x dx's derivative integral is ln x. So it's 5 ln x plus c. As I said, strictly speaking, I should put the... Hello, careful. Slides are there. Okay. So strictly speaking, in mathematics, I should put the absolute signs there, but I don't think that's very common because, especially in economics, you hardly work with negative values for x. So it's a little bit sloppy, but it's fine. Last function. Now, this one looks quite scary and complicated because it's a division there. So if I was to differentiate something like this, I would need to use the quotient rule. However, it's just x. So I can use some algebraic manipulations with the powers, and then I will be able to turn it into something simpler. So before integration, I can write this as x over x to the 4 over 5 dx. And then I remember that when I've got the same basis, but I'm dividing the function, indexes, I just have to minus the indexes. So that will be integral x to the 1 minus 4 over 5 dx. Now 1 minus 4 over 5 will give me what? One is 5 over 5. 5 over 5 takes 4, minus 4 over 5, just going to give me x to the 1 over 5 dx. And that is now just a very, very simple power rule. All you need to do now is x to the 1/5 plus 1 over 1/5 plus 1 plus the c. So a fifth plus 1. 1 is again 5 over 5. So together it will be x to the 6 over 5 over 6 over 5. And again, as we used in the previous example, dividing by a fraction, you just multiply by the reciprocal. So this will be 5 over 6 times x, which root and what power? What will be the root and what will be the power if I wanted to rewrite this as root and power form?
5
Fifth root?
5
and 6 plus the c, which is so easy to lose. Just try to train yourself not to lose the c.
Is it okay if you just kind of like just add it at the end? Do you have to add it consistently through?
Strictly speaking, you should add it consistently, just simply because if you're not adding it consistently, it's very easy to forget it at the end.
Why do you have the 6 before the square? It's not 6 versus 6 over 5.
Dividing by a fraction is multiplying by its reciprocal, which is turning it upside down. Okay, so I had to turn the 6 over 5 upside down. Strictly speaking, because if I keep that equation, because it's, I'm saying everything is equivalent, equivalent, equivalent. If I don't put the c's in here, that they're not equivalent. Yeah. They're not equal to each other. Just try not to forget the c. Okay, any more questions about these basic ones? Okay, now, same basic types of basic functions, but now with the definite integrals. When we are evaluating them between two limits. Hello. Slides here. Okay, where is my register? So anybody who came a little bit late, please do sign it. Okay. Now, what's going to happen in here? What is the rule? What changes once you start to talk about definite integrals rather than indefinite integrals?
Definite,
You're basically restricting your function into an interval. So you still need to remember the rules of integration, so I still need to know what will be the function, but with definite integrals I'm going to end up with a number as a solution rather than a function family. So what I need to do here, now remember the constant can be brought out in front of the integral sign. So I can write this as 1 over 5 times integral minus 1 to 4 dx. Now, what was the integral of dx? X. Because this is 1 here, and if I differentiate x, that's when I end up with 1, therefore 1's integral will be x. And now here comes the notation. You've got these square brackets. You write the function, remember this is now capital F of x in here, and then you write down the limits, minus 1 and 4 into here. And the last step in the calculation, now you substituting back 4 and negative 1 into the place of x. So 1 over 5 times 4 minus negative 1. And that's going to give me 1 over 5 times 5, which is going to be 1. Okay? Now, that was one of the functions. So it was function number 1. Function number 2, integral 1 to 5 x cubed dx. Okay, there's no constant that I can bring out, so I don't have to worry about that one. X to the 3, that's a power function. So what's the rule of the integration here? X to the 4 over 4. You're adding 1 to the power and you're dividing by that extra power. And that's you calculate between 1 and 5. So that's basically 5 to the 4 over 4 minus 1 to the 4 over 4. And here is when having a scientific calculator will pay out, because now you can just put those numbers back into the calculator and calculate the final value quite quickly and easily.
With the limits,
Yes?
would it make absolutely no sense if they were inversed?
It would, but what happens? If I have got integral ab fx dx and I change the limit,
Then you're minusing one from the other way, right?
yes, so I need a negative in front.
Okay.
Okay, so you can do that, but by switching the limit, the whole integral gets negative,
Yeah.
gets a negative sign in front.
So it just makes sense that the upper limit is always on top.
The upper limit is always on top and the lower limit is always at the bottom. Otherwise, you have to reverse it using a negative. Okay, so people with scientific calculators, because as always I've forgotten mine again. 156. Okay, last of this type. Okay, so x to the negative 1. I always like to rewrite that as 1 over x, because then I can remember that the integral of 1 over x is ln x. And again, top limit top, bottom limit bottom. So what I actually need to calculate now is ln 15 minus ln 9. And again, anybody with a calculator? I mean, I can leave it like that, because those are perfectly normal numbers. Those are actually exact numbers.
0.5. 0.5.
Yes. Yes. Okay, so it's 0.51. Oops. And remember, with the definite integrals, you're always looking for a number to end up with a number, because that's basically telling you what's the area under that particular function within those intervals. Any questions? Okay, so I hope everybody's kind of warmed up now. And here are a couple of more rules. Okay, as I mentioned previously, the constant can be brought in front of the integral sign. That's not going to make any difference. But that again also means that the constant number can be brought in to the integral sign, behind the integral sign, which is quite a good trick to know, because sometimes we can use that to our advantage when you're manipulating integrals.
What do you call the rule?
I call it constant rule, but other than that, I don't know what's the official number. I mean, official name. Now, the sum and difference rule, again, is the same as for differentiation. You can differentiate them term by term. Therefore, because the integral is antiderivatives, you can, again, integrate them term by term. And these properties are inherent from the equivalent rules of differentiation. Do you just want to open it up and then...
Seriously.
Did you call them and say that you don't have any loud food today?
Okay, right. Now, let's look at these rules and start to combine and do a little bit more funky integrals. Okay, so every time when you see a complicated integral like this, as soon as there is add or subtract sign in between them, you can break them down into terms, different terms, and that way make your life easier to do the integration. So, and again, because there are constant numbers in here, I remember that the constants can always be brought in front. So I can rewrite this as 3 times integral x to the 4 dx. Don't forget that you need to bring in the dx as well, plus 4 times integral x to the minus 5 dx. Now, those two integrals look a lot more friendly, because they're just simple power rules. And you can just apply that rule term by term. So that will be equal to 3 times x to the 5 over 5 plus 4 times x to the over negative 4 plus c. Okay? Don't forget the plus c. So what you can see here now is that the 4 cancels out. So at the end, it will look like 3x to the 5 over 5 minus 1 over x to the 4 plus c. Right, what's your feeling about number 2?
It's not too bad.
You just have, can you just, can I just say,
Mm-hmm.
thinking about it, can I just put the square root on its own? as a minus. Looking at indices and
Yes, yes.
can you have that x3 plus 4x, that's the, with the s, minus the s square root of x, that way dx? Can you have the minus on top?
To bring up the...
Times it by x and a half.
Yes, yes, you can.
It will be a minus a half. Minus half.
Okay, we can go down that route. Okay, we can try it that way. So basically, this function can now x cubed plus 4x squared over root x dx. What I can now do, I can rewrite this as x cubed plus 4x squared times x to the minus half dx. Yes, that's perfectly fine. I can do it that way, but that's still a multiple. And I don't know anything about multiples so far.
You just multiply it out.
Exactly, you just multiply it out. So that will be then integral x cubed times x to the minus half plus 4x squared times x to the minus half dx. And again, I can use the rules of indices. And if I multiply the same bases together, what do I need to do to the powers? Add them. So this will be x to the well, I'm going to keep it as 5 over 2 rather than 2.5 plus 4 times x to the
1 over 2.
positive half, because this is 1, take one end negative half gives you positive half dx. And now I can separate them. Integral x to the 5 over 2 dx plus 4 times integral x to the half dx. None of the powers are negative 1.
Oh, it's squared.
Yeah, we missed out the squares.
Plus 4.
Thank you.
That's going to be
So that's not,
just what? It's not going to have any.
that is 3 halves. Okay, thank you very much. Eye of an eagle. Okay, so now I can just use the normal power rules because none of the powers are negative 1. So it will be x to the 5 over 2 plus 1 over 5 over 2 plus 1 plus 4 times x to the 3 over 2 plus 1 over 3 over 2 plus 1 plus c, the annoying plus c. Okay, 5 over 2 plus 1, 7 over 2. So x will be 7 over 2 over 7 over 2. That's the first term. The second term, 4 times, what will be the power of x? 5 over 2 over 5 over 2 plus c. Again, dividing by a fraction, multiplying by the reciprocal. So I'm going to turn 7 over 2 to 2 over 7 times x to the, I'm just going to leave it as a fractional power for now, 7 over 2 plus 4 times 5 over 2, turn it upside down, will be 2 over 5 x to the 5 over 2 plus c. And then one last thing I can do is this fraction now will be 8 over 5. And I'm just being too lazy and run out of space, so I'm not going to copy it again. But the final answer would be 2 over 7 x to the 7 over 2 plus 8 over 5 times x to the 5 over 2 plus c. And you can leave it like this, or if you feel like, you can rewrite it as a root. 4 times 2 over 5, not x.
Sorry, can you just remind just writing? Because I always tend to just finish there. And well, do you mind showing us like how what you just said about writing it there?
What do you mean?
Like when you multiply that.
Yeah.
Simplify.
When you simplify it. So that 8 over, that's going to be 8 over 5.
Yeah. And that's it. I mean, the power is not changed from here. It's just the numbers now that you play around with. Okay, and we've got one last question. Oh, before I forget, the other way I could have done it, is that I know that there is a sum in the numerator and it's divided by one term. Just one term. It only works if you only have got one term. But what I can do then, separate the integral out into x cubed over root x plus 4x squared over root x. And that way, I would end up with exactly the same answer, but I could do it that way as well. So I would be able to avoid this extra step here, but I would still have to do 2 steps. Because I'm probably going to write it here.
Actually, it's still been the same thing.
Exactly. So x cubed over root x plus 4x squared over root x. And then you know that root x is x to the half.
So you're still going to end up doing
Yeah. And then again, dividing them, take it away. So I will end up with x, was that 5 over 2? Plus 4 times x to the 3 over 2.
Yeah, because you're skipping it.
It's one step less, but the final answer is exactly the same. So it doesn't matter which one you pick out first, you will end up with exactly the same answer. So problem solving in mathematics, different routes, but still lead to the same answer. Okay. Is that all right now if I wipe the board off? Okay. Okay, so last question on this slide. So again, there is a difference here, so I can separate it and integrate it term by term. And there is a 5 in here, so that 5 can be brought out. So, what's the integral of e to the x? E to the x, that's nice and simple. What's the integral, oops, stop, plus minus. What's the integral of 1 over x? ln x plus c. And that's actually the simplest of them all. Yes, yes. So mathematics can be quite deceiving now and again. What you think is simple can turn out to be complicated, and what you think is complicated can be quite simple. Okay? Right. Now, what's going to change if I have got similar examples, but with definite integrals? Yes, at the end, but just at the end. The rules exactly the same. Now, it really, really depends on how familiar you are with integration. And up until you become very, very familiar with integration, I would really discourage you to try to do a sum of integral in one go. So what I'm going to do is the long-winded way, and it's probably not what your teachers show you. But I think it's a good practice until you become familiar with the whole method to sort of stick to doing them step by step. So all of the rules that are true for indefinite integrals are hold for definite integrals as well. So I can integrate them separately, and I can bring out the constant multiplier to the front. So I can rewrite this as 3 times integral between 2 and 5 x to the 4 minus 4 times integral between 2 and 5 x cubed dx. So that will be equal 3 times square bracket. What's the integral of x to the 4?
X to the 5.
Yeah. And now I will have to evaluate that between 5 and 2. Minus 4 times. What's the integral of x cubed?
X to the 2.
And again, I have to evaluate that between 5 and 2. So it will be 3 times 5 to the 5 over 5 minus 2 to the 5 over 5. Take away 4 times 5 to the 4 over 4 minus 2 to the 4 over 4. And again, if you have a scientific calculator, you would give me a value. Anybody feels like calculating it? No. Okay, if I did the calculation correctly, this should be 2 1 decimal. Is it 2 1 decimal places? No, it's probably an exact answer actually. Now, one thing you can probably spot here, which would make your life a little bit easier before you put it into the calculator, is that the whole bracket is being multiplied by 4. But both of the terms inside are divided by 4. So these cancel each other out. But it only works if both terms have got the same denominator, which they will because it's coming from here. Did you get the same answer?
Yeah. Yeah. What did you get? 1, 2, 4, 6, 4, 8. Only one at a time.
Okay, so the next integral, I'm going to follow the same rule again. And I'm going to bring the 3 out. Integral 0 to 1 e to the x dx minus integral 0 to 1 x squared dx. By the way, why don't we need the c here?
Definite.
Yeah. But how does it become just one number now? What happened to the c? Exactly, because you got fb minus fa. So you would have plus c minus c. That's why the c disappears. Okay, so rules. What's the derivative of e to the x? Sorry, what's the integral of e to the x? Is it itself? Yes, between 0 and 1. Minus.
X to the cube, x to the 3 with 3.
Yeah.
1, 0.
Okay, now what I've got here is 3 times e to the 1 minus e to the 0 minus 1 cubed over 3 minus 0 cubed over 3. What can you tell me about this term? Okay, that's 0. What can you tell me about this term? Is 1. Okay, so don't forget, any number to the 0 power is always 1.
What about anything to the power of 1?
Anything to the power of 1 is itself. Okay, so what I've got here now is 3 times e minus 1 minus 1 cubed is just 1 minus 1/3. So 3 times e is 3e minus 3 minus 1/3. That is 3e minus 3 is 9/3 minus 9/3 minus 1/3 gives me minus 10/3. and I can put that into the calculator, or I could have put that to the calculator in here, and I should get an answer of 4.82 to 2 decimal places. Okay, I'm gonna need some space, so I'm gonna just wipe up the top one. And then look at the last example on the board. Now, this is again a fraction when I have got a sum at the top. Okay, so again, what I can do, I can break it out to two fractions, a sum of two fractions. So, if I break it up this way, then what do I end up in here? 1. And from now on, I can just apply the rules of breaking them into separate integrals. So that will be integral 1 to 2 dx plus integral 1 to 2 1 over x dx. Now, what's the integral of 1 dx or just dx? X itself. That will have to be related between 2 and 1 plus, what is the integral of 1 over x? ln x again. 2 to 1. So, what I've got here is 2 minus 1 plus ln 2 minus ln 1. 2 minus 1 is 1. What is ln 1? 0. ln 1 is 0. Because what power do I need to raise e to end up being 1? 0. So it's 1 plus ln 2, which should be roughly 1.69. Yeah?
So you definitely solve to the end.
The final number. Yeah. I mean, strictly speaking, 1 plus ln 2 is a more exact answer than that one, because I'm rounding in here. So, depending on if you need to do any more calculation with this specific number or not, I might round it or might not. If it's practical question, like, you know, what is the sort of sum or surplus or whatever kind of questions this comes up with, you're obviously not going to leave your answer as 1 plus ln 2, because that doesn't make any sense to the customer. So you would change it into 1.69. But other than that, it's kind of as and when. Which one's better and which one's not. Depends on the individual circumstances. Right. integration by substitution. Okay, now that's one method that you need to be quite familiar with, and if you're not, there is a video that you can look up and sort of go through quite a few more examples that the specific person using in that specific video. I quite like this, the math tutor side. They're pretty good at explaining what and why. So let's look at, okay, actually if you look at it, what do you notice in here? What is this formula coming from? Chain rule. Chain rule. So the integration by substitution is the backwards chain rule. Well, it does, but it's basically the method when you undo the chain rule. Okay, so let's look at some examples. And I picked up quite a few examples. I mean, I might have been overly ambitious with how many examples we can do.
I don't mind, compared to the assignment.
I'm tempted to only look at it after Christmas, so during Christmas.
So if I start to run out of time, I probably will have to drop a few of the later examples. But I try to be doing as many examples as possible. Okay, so what is the point of the substitution method? Well, the point is to be able to solve the integral, yes, so undo the, okay. What are the steps in the substitution method? Why is it called substitution method? So you introduce, so you introduce a new variable, usually u, and you substitute the difficult bit for being u. So in this case, the 5x plus 4, because if I had just e to the x, well, that would be very easy to solve.
Yes.
But now I introduced a new variable, u, so I cannot integrate by x anymore either. So what I need to do now, I need to find du dx, which is 5. So that tells me, and from now on I can treat this as two separate variables, and I can rearrange this equation and express dx as a function of du. So I could say du over 5 is equal to dx, and I can now substitute the dx as well as the u into the function. So now I can write this as e to the u, and dx is du over 5. My question.
I don't understand du. Oh, yeah, because that is cos dx, yeah. You just cross multiply.
Yeah. Okay, now this is 1 over 5 that I can bring out in front. And what's the derivative of e to the u du? Sorry, integral? E to the u plus the notorious c. And this is the last step. Now you substitute back u. What was the original? And that's it. That was example 1. Okay, so to summarize, you look at your function and you start to think about it. What would be the simpler version of it to integrate? Well, if there wasn't any complication in there, I would integrate it much easier. So, the 5x plus 4, I'm going to substitute to being u. And because I substituted u, I need to find now what dx is as a function of du. So I'm just going to differentiate du dx. That's the derivative will be 5. Rearrange this and express dx as a function of du. And pick up both of these, substitute back into my original integral, solve it that way. Once I've done with the integration, put the newly introduced variables value back, and then that's your integral with the plus c. Okay, now I have no idea how Arina showed you these integrals. Might have been a slightly different way. I don't, unfortunately, I'm not sure.
Too quick. Too quick. I can't remember doing it either. But no, it's right, that's the thing. She's talking. I'm like, yeah, that's it. It's too quick. That's all.
That was
Right,
like
7 pages an hour.
Okay, let's look at the next function. Okay, well, I can see here that this is a power. So if I had just a simple variable here, one variable here, that would bring me back into the very simple and easy x to the n kind of integral. So I'm going to introduce the new variable, u being equal 3x plus 2. So I can rewrite this as integral u cubed, but I cannot integral with respect to dx anymore because I introduced u. So now I need to find out what is the new variable of the integral. So du dx equals 3. So from this one, du over 3 equals dx. And now I can substitute instead of dx the du over 3. And again, I can bring the 1 over 3 out. And what's the integral of u cubed?
u4 over 4.
Plus c. So 1 over 3 times u4 over 4. So in the denominator I've got two numbers but need to multiply together. So that's going to give me 12. 3 times 4. And u is 3x plus 2 to the power of 4 plus c. Wow, with the simple ones it's not. Okay. Okay, number 3. And again, I'm not, did you have to do integration by substitution and definite integrals?
He's going to teach us.
Teach us everything.
Okay.
I'll look at my assignment and I'm saying, just teach us everything.
Okay, so first of all, what I'm going to do is obviously rewrite this as a power because otherwise I can't really see what's going on. And that's to the quarter of the power. Okay, now obviously if I didn't have that 7x minus 16, if I just had a variable there, variable to a power, it's easy to integrate. So I'm going to introduce u being 7x minus 16. But then I need, dx. So du dx will be 7. Therefore, dx is equal du over 7. So far, nothing changed. So I'm going to do integral, but the difficult part comes here, because I now introduced a new variable. I introduced u. So that means this is x going from 3 to 7, but now I need u going to 1 from what? So I need to use this, what I introduced, and calculate the new limits of the integral, because I have got now different variable. So when x was 6, u will be 7 times 6 minus 16. I'm going to cheat. And that I'm not going to cheat because I made a mistake in my calculation. So 42 minus 16 is
26.
26. So the upper limit is 26. And the lower limit, x equals 3. So u will be 7 times 3 minus 16. That is 5. That is 5. And I haven't made a mistake, I just misread my paper. That's 5. Okay? And from here on, I'm going to make a star here, so we know that it follows on from that. The 1 over 7 can be brought out. U to the 1/4, what will be the integral of that? And it will be evaluated between 5 and 26. And the easy part in here is that you don't have to substitute x back. You can just calculate straight using the u. Yeah, because I've changed the limits now. Oof, that looks quite a bit horrible. So it's 26 to the 5 over 4 over 5 over 4 minus 5 to the 5 over 4 over 5 over 4. And if I have not made a mistake by doing the calculation, it should be 5.86 to 2 decimal places. Okay, do double check it because I tend to make mistakes. So.
Sorry, the 1 over 7 at the front bit.
Yeah.
I've lost how we get it. Is it just from the du over 7?
Yeah.
We just bring it to the front.
Yeah, and we just bring it out to the front. Okay, so that was example 3. So let's look at example 4. Integral 1 to 3 2x over x squared plus 7 dx. Yes, substitute again, because it's still a substitution method. But what are you going to substitute now? Well, yes. I'm going to use x squared plus 7 to be my u, because that's the more complicated part. But I'm also doing it because I've noticed that x squared's derivative is 2x. And don't forget that the general rule was integral f of g of x times g prime of x. Just go back to that slide one before. This one. F at g of x times g prime of x. So you can use the substitution method when you've got that g prime of x there. And the 2x is the g prime of x. So, and the 2x is the derivative of this. So that's another telltale sign of using the substitution method. So, therefore, du dx is 2x. So, rewriting this, dx is equals du over 2x. So, integral 1 to 3, 2x over u times du over 2x. And how convenient. Okay? So what I've got here is integral 1 to 3, 1 over u du. Oops.
Yeah, I'll find a new limit.
I need to find a new limit. So x was between 1 and 3. So if x is equal to 3, u is equal to 3 squared plus 7, that is 16. And if x was 1, u will be 1 squared plus 7, which is 8. So it's 16 and 8. Okay? Now, what's the integral of 1 over u? So that is ln 16 minus ln 8. And I'm going to have to write down, I don't know where to, here. So the final number will be no, ln 2. You probably haven't closed the bracket in the first log. Very common mistake, don't do that in the exam. This is ln 2 because subtraction between log signs, meaning I can divide the numbers, and 16 divided by 8 gives me 2, which is 0.69 to 2 decimal places. Okay. Is everyone happy if I rub the whole board off, or do you still need the bottom bits? Okay. Now, this one is a very tricky one, but I think it's a good example. So,
Next, just think, you make the 2x, you. It's
The one at the top is more difficult. So make
I mean, if I make 2x to u, then I would have e to the u over 1 plus e to the u over 2. That doesn't seem to be any simpler at all. Somehow I want to get rid of the e to the x altogether. So, one thing that I notice here is that e to the 2x is nothing else but ex squared. Now, that means I could actually choose u to be e to the x. Can I rub the rest of the board off now?
Yeah.
Although it seems that it's probably not going to be very useful at the moment. But maybe it's going to lead me somewhere. And that is where integration starts to become difficult. While you've got the derivatives, you just follow the rules blindly and you can differentiate whatever. Integration not as straightforward. So some functions you have to try, doesn't work, try another way, doesn't work, try a different way. It might still not work. Very positive outlook on life, isn't it? So now, if I chose u to be e to the x, then du dx is e to the x. So the x will be du over e to the x, but that is du over u, because I've chosen u to be e to the x. So using this little trick, now I can rewrite this as u squared over 1 plus u times du over u. So that was the whole point, because now I can cancel them by 1u and I could get rid of the square. So this will be integral u over 1 plus u du. Okay, what am I going to do with it now? Now here comes another very standard trick in mathematics. What I can do, I can add 1 and take away 1 to the numerator. Because add 1, take away 1 is 0. So I've done nothing to the numerator. But it's good for me, because then I can break this into two parts. Integral 1 plus u over 1 plus u du plus, not plus, sorry, minus, integral 1 over 1 plus u du.
Can't you just split it out?
Hmm?
Can't you just say u over 1 plus u over u?
No, you can't do it to the denominator. You can't split the denominator into two. You can only split the numerator. Unfortunately, that would be easier. This trick here.
Would that not make it minus 1? That's that.
Well, yeah, it's going to be 1 and...
Minus is there already.
Minus is here. I just brought the next.
No.
What's the minus?
Not minus 1 here.
She just should put
Yeah,
it.
so it's minus 1.
Yeah, she just should put
So plus 1 minus 1 altogether makes a 0. So literally I added 0 to the numerator, which means I have not changed the numerator. I just wrote it in a slightly different manners. And then I can split this. Let me use some different colors. Then I can split this using, oops, totally screwed it up. Right, so. So I can split it this way, which becomes here, and the other one is this one. Which becomes that.
So if you don't do that, would you just bring that up and expand the bracket?
How do you expand something to the -1 power? Because if you were to rewrite that, it would be u times 1 plus u to the -1. How do you expand that bracket?
Alright, okay.
You can't. Okay? Not even using the binomial theorem because it's not true for negative powers. This is the only way to solve this integral. And unfortunately, there are some integrals that you sort of have to solve it one way and you can't solve it in any other ways. Okay, so what I've got in here now, 1 plus u over 1 plus u, that is just 1. Oh. And what is the integral of 1 over 1 plus u? ln 1 plus u. Plus the c, but I forgot to do this one. Integral du is u. Oh, why am I writing plus all the time? So it's u minus ln 1 plus u plus c, but I started with x's. So I need to bring back now what was u, so it will be e to the x minus ln 1 plus e to the x plus c. Now when you have got these sort of integrals, which quite frankly relatively complicated, then what you want to do is look at this function, differentiate it again, and see if you end up with the original one. And then you can try that at home, and hopefully you'll end up with the same function that we started with.
The first one, could you just, the 1 plus you bring it up?
What, where?
When we have
Here.
u, yeah, 1 plus you just, yeah.
We've been through that in a minute ago, because u over 1 plus u then equals u times 1 plus u to the -1. And what you're going to do after that? Then you come back into here. So if you have got these kind of things, add 1, take away 1. If it was another number, what would I do? If it was, let's say, 2. Add 2, take away 2. Okay? Pretty much that you're going to have practice questions like this. But I just wanted to show you the integration is not as straightforward. It can get quite tricky. Okay? One more very, very standard method of integration is integration by parts. Now, the u substitution or integration by substitution was the antiderivative of the chain rule. This integration by parts is the antiderivative of what rule? No, not the quotient. What do you have here? Multiples all the time. So it's the antiderivative of the product rule. Okay, so it's the other alternative of the product rule. Again, I suggest you have a look at the video again to just see some more examples. Right, I can't remember now which notation Arina used. Both of them quite standard. Basically, I'm just replacing the derivative of v with v prime, which is, again, just the derivative of v. Okay? For this one, you just need to remember this rule. Integral uv prime dx equals uv minus integral v u prime. Right, when you look at the formula, what can you see between here and here? What happened to the prime? Switched. So as long as you start with one of them being a prime here, they both without the prime here, and in the second term the prime switches. So whatever was not differentiated here will get differentiated here. When do we use the product rule? When by differentiating one term in the integral, I would end up with a slightly simpler integral. And obviously it has to be a product of two functions. And whichever I'm choosing to be u and v prime is down to me. If it doesn't work one way, I've probably chosen the wrong function to be u and v prime, so I can try the other way. Where am I now? Oh, that's it. Okay. So in the first example, I have got integral x e to the 5x dx. What I see here is a product of two functions. So I know I can use the integration by substitution. The next question is, I'm just going to write the rule here. The next question is, what do I want to be u and what do I want to be v prime? Now, if I look at here, u gets differentiated in the second term. So I should choose the function which gets simpler once I differentiated it. So if I differentiate x, that becomes simpler, because if I differentiate e to the u, or e to the x, 5x, whatever, that doesn't get simpler. So u will be x, therefore u prime will be what? 1. Okay? Now that leaves me with a slightly complicated question. V prime was e to the 5x. What is the original v then? What is the function that I need to differentiate to end up with e to the 5x? E to the 5x. Okay, if I differentiate e to the 5x, okay, y equals e to the 5x, what will be the derivative?
Oh, sorry.
5x multiplied
5 e to the
5x.
So almost e to the 5x, what do I need? E to the 5x over 5. Because if that's the case, then the over 5 will cancel out. Okay? So that is e to the 5x over 5. So, right. So, following on from there, u times v, that is x times e to the 5x over 5 minus integral u prime, which is 1, times v, which was e to the 5x over 5 dx. So x times e to the 5x over 5, I can write it that way as well. Now I just need to think about that integral. How would you do this type of integral? I can bring the 5 out in the front. And if I just look at, I ignore everything else, if I just look at this type of integral, what would be the solution? How would you do it?
5 over 5.
There is the 5 in there.
You have to use what?
Okay. Right.
Could you make it?
Okay, the standard method for this type of equation, these type of integrals would be substitution. So now I'm not going to use u again because I've used u already. So I'm just going to bring up another variable, and I'm going to call it t. Okay, so t is 5x. So dt dx will be 5. So dt over 5 equals dx. So that's the same. That is e to the t dt over 5. So again, I can bring the 5 out. X e to the 5x over 5 minus 1 over 25, because 5 times 5 gives me 25, integral e to the t dt. And what is e to the t dt integral? E to the t, because there are no constants now. So I can just integrate it simply. So that is equal to x e to the 5x over 5 minus 1 over 25 e to the t plus c. And again, I will be very lazy. And because I have got the whiteboard, I can just simply wipe the t out and put 5x there. I just don't have more space to write it out again. And that is, again, the integral. Yes. Yep.
You have to substitute t. So far, you said t equals 5x. Like you just integrate that. But no, we just be 1 over 25.
What do you mean? I mean, if you look at this to here, because that's the derivative, that's the antiderivative, so I could have just used that and put that into here. Question is, would you notice that? That's why I'm kind of telling you the standard method, that if it looks like this, use the substitution and then you're on the safe way. Once you get used to what the integrals look like, you're probably just going to say, oh well, that's just the antiderivative of this, so the integral has to be equal to that one. But that really depends on how many examples you've done. Okay? Right. I'm going to have to skip number 2.
Number 2?
Yes. Because there's an extremely similar example in the assignment. So I'm going to do...
Why are you skipping it? I don't understand.
No. I can't do it because it's basically the same example.
But is it the same example?
Exactly. I can't remember now which one. I just quickly looked at it and said, ooh.
But is it the same question?
Pretty much the same question.
But is it the same?
Same question, yes. It is the same question.
If you change the letters, does it count?
But we kind of done it. We kind of done it anyway, because look.
It's the same thing, it's just because it's a constant.
Yeah, but there is a twist. That's 0 to 1, so that's why I'm not going to go through that.
So basically, you just find the new limits then?
You figure that out at home. Okay?
You don't have to say anything, just nod.
Okay. Let's look at number 3. Right.
You're messing with me, man. You're the I gave up.
Your job is to be positive.
All we need
I was finished. I was out.
No, just have you. Apart from Mr. Southwest Trends, I need him in my life.
What am I doing with my papers?
Killing me, eat his brain. There you go.
Oh, I'm picking up the wrong ones. Yeah. Okay, this is the one I need. Right. Okay, so integral x squared. Okay, so again, why are we going to use the integration by parts here? Because it's a product of two functions, and on top of that, one of the functions will get simpler if I differentiate it. Which is that function? X squared. So, again, the rule, integral uv prime equals uv minus integral u prime v. Okay, yes. Yes, you have to do it twice. Okay. So, what am I going to choose u to be? X squared. So u prime will be 2x. And then v prime is e to the 4x. So what is v?
E to the 4x over 4.
Yeah. Exactly the same way as we done it with the previous one. So, this is now equal u times v, which is x squared e to the 4x over 4 minus integral x times e to the 4x over 4 dx. So again, I'm going to do u1 being x, u1 prime being 1, v1 being, again just going to do that e to the 4x, v1 prime, and then v1 will be again e to the 4x over 4.
She's doing it again.
Yes.
Let's say try to get 1x. So it's 3 times that, 3 times.
So u1 times v1 gonna give me x times e to the 4x over 4 minus, remember that 4 I brought out, and then what's left behind is x times e to the 4x, but now x's derivative u prime is just 1, so that's going to be integrate e to the 4x over 4 dx. So before I'm going to deal with this last integral, let's make it slightly more friendly. So this is
Is that 1 is a constant 2 minus 2a? Because if I'm using u prime minus 2a. Is that right?
yes. Oh, right, I lost it. Okay, so u prime was 2x. So that's supposed to be 2 here. And that also means, so that is cancelled down, so that is just 2 in here. And that again cancels down just to 2 in here. Right, let's just okay, I have to start over because I just can't see now what's going on. So, okay, right, before I bring in these u's, okay, so the original was now x squared e to the 4x over 4 minus a half times integral x e to the 4x dx. Okay. Right, so u1 now going to be x, u1 prime will be 1, and v prime is e to the 4, so v1 is e to the 4x over 4. So oops, not integral. So now I'm going to use the substitution again. Sorry, not the substitution, the integration by parts again. And it's u1 v1 x times e to the 4x over 4 minus integral u prime, which is 1, times v, which is e to the 4x over 4 dx. Okay? So I've got a bracket in here. Let's try to break that up. Minus a half times positive quarter gives me minus 1 over 8, or x e to the 4x over 8, minus, bring that 4 out, multiply that by a half, so it's going to be 1 over 8 times integral e to the 4x dx. And then what would you do now? I still have got e to the 4x, so I'm going to use the substitution again. So t going to be 4x, dt dx going to be 4, so dx is equal dt over 4. So the first two terms does not change. So this stays the same. I'm just going to use that to being a star. So you've got star plus, not plus, minus 1 over 8 times integral e to the t dt over 4. So those two terms at the front minus the last integral, and that is equal again still the star minus bring out the 4. That's 1 over 32. E to the t dt, the integral here, e to the t, what was t? 4x. So the final answer to this integral, just so everybody got the whole thing written out, is x squared e to the 4x over 4 minus x times e to the 4x over 8 minus e to the 4x over 32 plus c.
Is it likely in the exam that we'll get a part followed by a
Substitution.
Yeah.
Does
she tend to like doing?
Have a look at the past exam questions and the mock exams, because that will be the best indicator of what kind of questions might come up. I think this x squared times e to the something x, it's probably have been.
But is this the highest? Because it doesn't get executed, right? To do it 3 times.
I don't think so. I don't think so. I don't think so. But
because surely, essentially, once you've got 2, 3 is the same thing, but you just it's no more. It's no
yeah,
more.
I mean, what's actually going on in here is, you know, this one we effectively done this one with the 5x. So you can just sort of follow those steps there.
But yeah, so like a 3-part one would be no harder, just more work.
No, it's just yeah, just one extra step doing the same thing over and over again, which is, if anything, boring.
Yeah.
Not difficult, but just boring.
Fine by me.
Okay, let's look at the last one, number 4. Is that all right if I rub the board off?
Yeah.
Well, yeah, when they shatter your world in the first day of year 7, they're like, everything in there is a lie. Always lies. I bet you if you do a master's in that, by the way, lies.
Every level you step up is all lies.
First day, like, give me my £9 grand back, I'm off.
PhD level, you get to do all your own ones.
To write your own lie.
Okay, right. So how do we integrate log of x?
Ask it very kindly to do it. So.
That's differentiation.
Yes, exactly.
That's differentiation.
You're doing anti-derivatives.
X over 1.
All right. Well, there's no rule for
Yeah.
following the ln x, simply because there's a trick that you can use to differentiate a log of x. So if you think about this specific function, that is integral 1 times ln x dx. And that's the standard way of doing the integral of the log x, ln x. And now that is a multiple of 2 functions. Quite hard to say. quite unnaturally. But now I can think about U's and V's. So what would you choose to be U and what would you choose to be V? And why? Exactly. And then if you try to find out what's the antiderivative of ln x, well, that's what we're trying to do. So that would not work for ln x to be v prime.
Yeah.
So, because again, remember the rule is integral u v prime, oops, doesn't look like a u at all, equals uv minus integral u prime v. So you want u to be the function that gets simpler after you differentiated it. So if u will be ln x, then u prime will be 1 over x. That's much simpler than the ln x. But that means that v have to be equal to 1. And what is v prime if v is 1? X. That was relatively simple. So, now, so what I need now is u times v sorry, screwed up my notation. That's v prime and that's v. Okay, so v prime was 1 and then v is now x. So u times v is x times ln x. But because I'm doing a definite integral, now I have to evaluate this multiple between the limits. Minus, I've got a new integral now. And what is that new integral?
Sorry. The limits are 1 and 5?
Yes, the limits are 1 and 5. Thank you. Okay, so what will be here now?
1 over x.
Yes?
X.
1 over x times x dx. But isn't that handy?
Yeah.
So, I've got x ln x between 5 and 1 minus integral 1 to 5 dx. Which is basically x ln x between 1 and 5 minus x between 1 and 5. So that is 5 times ln 5 minus 1 times ln 1 minus 5 minus 1. Five times ln 5 minus ln 1 minus 4. Again, what do I know about ln 1? 0. So it's 5 times ln 5 minus 4, which is roughly 4.05, no, 4.05 to 2 decimal places. I'm pretty sure that in the exam, if you leave it in this form, 5 ln 5 minus 4, that would be acceptable.
I understand why she says people who don't come to this class.
Don't look on a class. Just forget it. I go to the class and I don't think I'm classy.
Worry about that when it comes to it. So, I mean, luckily, guys, you are in a sense a better situation than the management students because they have got 3-term teaching, so they have got exams every 3 months.
Honestly, I think this is going to get longer and longer. I'm going to forget this. If I don't keep it right,
How do I keep it?
Yeah, but how much time do you have between your last lecture? But they're my students.
Yeah.
But you're gonna have how much time between your last lecture and the exam?
I don't actually know.
Check it out, because I think you finish your last lecture around Easter, and the exams are probably in June.
May, June.
So I think
So
You have quite a lot.
so you have got,
But we do have.
and at that point you're not gonna have to go to any other lectures.
Do you reckon that if you keep doing your your examples and your problem sets, just to remind yourself, you should be all right for the exam?
Yeah.
Yeah, you should be. It's practice, but it's
Yeah.
just too much work.
Okay. I still have got more. Okay. It's long, isn't it? Right. So that was all the simple integrals, but we can we can make them even more complicated by thinking about the infinite integrals. Unfortunately, we do, because once it again comes to as expected values, probability, and the rest of it, you're going to have to integrate between negative and plus infinity. So you need to know what happens to integrals with infinite limits. And that's the definition. Okay? What happens if one of the limits is infinity? Yeah, pardon? So if the top limit is to infinity, then you just take the limit of the integral and then take away the bottom limit. And if the bottom limit is the infinity, then just calculate the value of the integral at the top limit and take away the integral going to negative infinity, the limit of the integral going to negative infinity. Now, what you can see here is that it was x here, but now I change it into y. Because the limit, I'm introducing a new variable, because the variable of the differentiation is different from the variable of the limit. Because that's basically now the top or bottom limit of your integration, not the variable anymore. Because basically what happens here now, I probably could have, maybe it would make more sense if I change it to b stands to infinity fb, because that's more kind of what you use to integral limits between a and b.
So what is going to be your answer? It will be positive or negative infinity?
Depends on the function. Depends on the function. Depends on the function. Now, if your final answer is positive or negative infinity, it means that the integral doesn't exist. There is, because there is no limit. But if there is a finite limit to this, then you can say that there is an integral that I can talk about.
This is the thing that we did the other day, where you have like 1 minus
Yeah,
1
yeah,
over
because
something
one has to
to
be
the...
positive or negative.
Yeah.
Yeah,
I
those
think
kind.
it's the opposite way it works.
Okay. Right. So. Yes. Okay. Let's look at examples. So, to solve this integral, I actually need to see what kind of function is inside there. So that's basically nothing else but integral 1 to infinity x to the minus 3 dx. Now, what does it mean to me then? What is the antiderivative of x to the minus 3?
X to the minus 4. Minus 2. X minus 2.
Yeah. So I've got x to the minus 2 over minus 2. Now, the top limit is infinity. So the top limit have to get to infinity. And this is where I'm actually not using the x anymore, but let's say b, because that was the top limit. So the top limit tends to infinity minus the bottom limit, which is 1. So 1 to the minus 2 over minus 2. So let's rewrite this in a form that is a little bit more sensible. So that is minus 1 over 2b squared.
And why do you put b there?
Because that was the top limit.
So it's b by default. Is it always b when it's
Any other letter than x. Hmm? It's negative 2 power. B to the negative 2. So that's why b comes down. Okay? Negative, negative gives me positive. 1 to the minus 2. Yes.
So the first one must be 0.
Why is the first one 0?
Including 1 over infinity.
Yes. But if you think about it, what happens to your b is gets bigger and bigger and bigger. So if you divide 1 by a bigger and bigger and bigger number, u tends to get smaller and smaller and smaller. Eventually you get to 0. So that is, and I don't know if this kind of notation have been used or not, but mathematicians quite often use it, saying tends to 0.
I think that's the only bit of notation that Arena hasn't used.
Okay, don't worry about that. So the overall limit of the integral is half. Now, here's another trick that I'm going to show you. Because what you see here is b is almost g prime of x. And remember, what we did with the integration by substitution, we had that integral f at g of x, g prime of x, will be your f at u at the end. And your u was the g of x. So, what I can do here, and that's very, very standard, if I had it minus b, then that would be exactly g prime of x. So, it's very standard that I put a negative sign outside, and I put a negative sign inside. Because negative 1 times negative 1 is positive 1, so I haven't changed it. And then, what will be this integral? E to the minus b, yes. So, the integral of this is e to the minus bx. Now, what's going on in here? The top limit tends to infinity, and unfortunately I already used b up, so I have to come up with another letter. So this time I'm going to use it y, and that is e to the minus by. Well, I had a negative in front of the whole integral sign, so I'm going to use it this way, minus e to the minus b x, and actually not x, just 1. Because the bottom limit for x is 1. So that's minus b times 1, which is minus b. Okay, so now I can break up the bracket and bring in the negatives. So it will be minus limit y tends to infinity e to the minus by, that is 1 over e to the by, and negative times negative gives me positive, that's plus 1 over e to the b. Now, as y tends to infinity, what's going to happen to this limit? So again, e to the x, when x tends to infinity, is infinity. But 1 over x, when x tends to infinity, is 0. So this whole limit is 0, which is quite handy. So the overall answer to this integral is just 1 plus e to the b. And obviously, depending on the parameter b, you would have a number there. But this is how you deal with it when it's a parametric version. Is it sinking in at all? It's almost 2.5 hours of mathematics now, and we gradually getting more and more difficult ones. So
does that only work because you know b is a positive number?
yes.
The lower limit is 1.
Yes. Because if b was negative, then the whole thing would come up again, and it would be infinity, and therefore that would not be.
Right.
Integral wouldn't work. Okay? Right, let's try the next one. Okay, number 3. Integral minus infinity 0, 3 e to the x dx. So I can bring the 3 out in the front. So what is the integral of e to the x? E to the x? So it's 3 times e to the x when x is equal to 0. So that's e to the 0 minus the limit of the bottom limit, which is a, tends to negative infinity, e to the a. Because that's your bottom limit now. So, what is going on in here? That is 3 times e to the 0 is 1, so that's just 3, minus 3 times the limit e tends to negative infinity e to the a. Now what is this limit? What does your e to the x function look like? So, if x goes to negative infinity, where does e to the x go? It's go this way. What is that tending to?
Negative.
X is tending to negative infinity. What is e to the x? What is y tending to? 0. So it's getting closer and closer and closer to 0, but it never reaches 0. So this limit is 3 times 0, which is still 0. So the overall solution is 3. So it's actually quite good to know about these functions, but be careful, because if x tends to positive infinity, then where does e to the x tends to? Infinity. So that end, it doesn't have a limit. But if it's coming down this way, it's got a limit. Actually, it does have a limit. We just can't deal with the positive infinity. That's just useless as long as practical applications go. Okay, so the limit of e to the x when x tends to positive infinity is positive infinity. And that's why, in that case, an integral like this would not have a solution, because the overall answer to the integral would be infinity. Okay, last of this type. Oh, okay.
Oh, have you got it? Okay, thanks. Never mind.
Let's start with this one. So, what do you think about this one? Now, what's going on in here? I mean, k is a parameter. So to start with, it's not a straightforward integral because you've got parameters in there. And on top of that, x and y are both variables. But I'm only integrating with respect to y. So it's like when you do partial differentiation. Doesn't matter how many variables are there, you only concentrate on the one that you do the differentiation by. So it's the same for the integrals. In principles, you can ignore x to be a variable and you can just treat it as a parameter again. So there are terms where x is present, and there are terms when y is present, and there are terms when both of them are present. So what I can actually do here, this one, I'm going to do it on the side here. This can be rewritten as e to the minus kx minus ky And then I can rewrite that as e to the minus kx times e to the minus ky. Just simple algebraic manipulation. Now, why is that good for me? Why was that good for me? Because what I can see now, the minus e to the minus, not cancel out, factor out. So these two terms do not have y in it. So I'm going to treat them as one integral. And here I can factor e to the minus ky out. And what's left if I did that factoring out? I left with minus 1 plus e to the minus kx, which I can just write as e to the minus kx plus, sorry, plus, not plus, minus 1 dy. Oh, I don't need that bracket.
Yeah, but is that going to be constant? Do we still need to write 1 minus e to the minus kx? Is that staying out? Or?
Exactly.
Oh.
Exactly. So that's a constant because it doesn't have a y term in it.
Yeah.
So I can factor, bring that out in front of the integral sign. And this one again I can bring out in front. Oops, what am I writing? So what can I do in here then? What is this integral? The integral itself. So that would be what, that is 1 in here. So what's the integral of 1? Y. So what I've got now is 1 minus e to the minus kx times y, and I'm going to use this alternative method because it's in between 0 and infinity. So at the moment I'm just not going to worry about the limits. And then what's going on with the second one? Now that's a little bit more difficult to see probably. Now, if I had the minus k in here as a multiple, I could use the reverse chain rule. And again, this is a very standard trick in mathematics. I could put the 1 over minus k here, and then in the integral, minus k e to the minus ky dy. Okay? Now, why can I do this? Because I can bring in and out of constants, and basically minus 1 over k times minus k is positive 1. So I strictly speaking done nothing to my integral, just rewritten it in a slightly different form, which makes it easier to integrate. So what will be the integral of this one? What's the antiderivative of this one? Yes, that's gonna come there because you have got that one there. But if you think about it, e to the minus ky, differentiate this with respect to y, that gives you minus k times e to the minus ky. So, and I'm probably gonna have to go, oops, that was 0 to infinity. To here now. oops, y.
Brain surgery.
Ooh. Goodness me. That's just not good. It is a sign that even a board gets tired. Okay. Now, think about the limits now. Now, remember that this was y, because we were integrating with respect to y. So all these limits for y. So look at this one. What happens to this term when y tends to infinity?
No, it goes massive.
It's y. Y gets bigger and bigger, gets to infinity, multiplied by a number. It's still infinity. So this term is infinity. Okay? When y is 0, then the whole thing is 0. So that part we don't need to worry about. So it's infinity minus 0. Okay, but that doesn't make any sense. Okay.
Sorry, how do you know there's not a minus on the bracket?
What?
The 1 minus e to the minus k.
It doesn't matter if it's.
Because then wouldn't it be minus 100
Well, that's just the constant multiplied by positive infinity. It's going to be positive infinity.
Right.
Okay. If x is negative, e to the negative k times negative x, that's e to the positive, that's a positive number.
So 1 minus that is a negative number, right?
Depends on the sign. Okay.
That's how it's
Yeah, all right. Okay. Eventually it gets positive infinity.
Okay.
Okay, and what about this one? That looks a bit more complicated, doesn't it? But then again, okay, maybe you would see it easier if you say it's 1 over e to the kx. Oops. Y. Between y equals 0 and y equals infinity. Okay, so let's look at this term then. Again, try to rewrite that. So we've got a negative in here. That means I can switch these two terms. Or just keep the negative sign, okay? Negative. Okay.
1 over e to the kx.
1 over e to the kx minus 1 over k. And that is 1 over e to the ky. Between y being infinity and y being 0.
So as y tends to infinity, that second part is 0. So the first part becomes multiplied by 0. So it's all 0 as y tends to infinity.
Yeah, that's good. So when y tends to 0, sorry, I probably just have to repeat that because I don't think it was heard in the video. So as y tends to infinity, this term down here gets bigger and bigger. 1 over infinity is 0. So that whole term is 0. And when y is 0, then 1 over k times 0 is 0. So 1 over e to the 0 is 1. So that's just this term. But because that's take away negative, this becomes positive. So plus 1 over e to the kx minus 1 over k. But I have got the infinity here. So what will be the overall limit of this function or integral? So yeah. So basically, this integral doesn't exist because it doesn't tend to an exact number, it tends to infinity. Yes.
For the third part of the question there, where you wrote, you separate them into two functions there. Where does the plus come from? The third one.
This one?
One above. The third one above. So yeah, where's the plus come from?
Okay, the plus comes from the fact that I switched these two. So minus e to the minus ky plus e to the minus kx minus ky. Swap them over. So it will be plus e to the minus kx e to the minus ky minus e to the minus ky. And then I can factor out the e to the minus ky, and the minus comes into here. Okay? Right. Economics application, because after all, that's why we're doing these things. Okay? So, what type of question is this? What value? It's a present value question. So what do you use to calculate these types of present value questions? Yes? After all, we're doing integrals all day today. So, what is the general formula for these types of integrals? Integral 0 to t c e to the minus rt dt.
I remember that, but not with the infinity. CER.
Okay, so what is c equal to in this particular question? Yes. What is r equal to?
0.08.
It would be nice if they're giving you 80% return. That would be lovely. And do we need anything else?
T. 20.
Capital T. And what we need to do now is put that back into the formula. So 0 to 20, 1000 e to the minus 0.08 t dt. Now, bring the 1000 out. If I look at this function, e to the minus 0.08 t, that is a composite function, because I have got not just e to the t, but e to the minus 0.08 t. Now I can either use the integration by substitution, or by this point now, I can probably see a trick. 20 years.
Oh, capital T, sorry.
Yes. Unfortunately, in mathematics, if you use lowercase t and capital T, that's two different things. So, if I had integral minus 0.08 e to the minus 0.08 t dt here, I could just find that integral being e to the minus 0.08 t, because that would be the antiderivative of the chain rule. The only way I can bring this integral to look like this, if I do this. Because then those two cancel each other out, so I've literally done nothing to the integral. Don't forget the limits. So that is equal to 1000 over minus 0.08 integral e to the minus 0.08 t between 0 and 20. And I'm going to have to continue up in here. So it's 1000 over minus 0.08 times e to the minus 0.08 times 20 minus e to the minus 0.08 times 0. So it's 1000 over minus 0.08 times e to the minus 0.08 times 20 gives me minus 1.6 if I have not made a calculation mistake. And what is this one here? That's a 0. E to the 0 is? Yeah. And now you just put that into the calculator, and hopefully doing the calculations correctly gives you 9,976.29. And don't ask me what it means, because I don't know anything about economics. It is thousands per year for 20 years.
Oh, per year. Yeah.
Mm-hmm. So that's present value at the moment. It's almost £10,000.
That's right.
It's a very, very small interest rate, isn't it? So. Okay. Probability. Have you done any probability? Have you done any? You already started it?
We already done.
Okay. And I don't want to scare you, but that's just going to get more complicated. The probability ones are more or less quite simple compared to the later ones, like the hypothesis testing and the rest of it. That's what really confuses people, especially if you haven't done any kind of statistics, because it requires you a slightly different way of thinking. You just have to get used to thinking about it a slightly different way, and then if you do, it will be fine. It's just going to be very scary at the beginning, because it's very, very different.
That kind of leads into the question I was going to ask.
Mm-hmm.
Our current level of panic and shock horror, how normal is that?
Absolutely normal.
Like what you've seen.
Absolutely normal.
Do you see people kind of like have panic attacks and then do well?
Yes.
Okay.
As long as you are willing to put the work into it, and not just in the last couple of days, then you'll be fine.
I took to
Oh, and then you're gone, so we're not fine.
Now we panic. Yes, now we panic.
But it's
Still
true.
gone wrong.
And she said,
Has
you
she-
know
has
what?
she found
You know what
someone
she's
yet?
saying? Like,
Have you found someone to fill your place?
Not yet.
No one can take her place.
Not
like,
yet.
not finding anyone is not helping.
Not yet. They're advertising for the position, but not at the moment.
You should just do videos and send it to us.
Scratch that.
Yes. Okay, right. So, the probability of a specific variable taking values between a and b is the integral of fxx between those two limits. Now, what is fxx in here?
Oh, actually, yeah, this is, Arena uses really mad notation for this that I never understand.
E thing with the man in the middle.
No, that's fine. It's just that she uses, so sort of bar x's in capital and small. She uses algebra x's, and then she uses little algebra x with a little hat on top. And I tried like 3 lessons in a row asking what each one is, and I never understand.
I have to look at her notes.
It's like this. I can't remember what you call it. Is it X beta or something?
No, it's,
That one with the hat.
Oh, x with the hat. X with the hat is the estimated value of x. That's different from x top bar and x bottom.
No, not bar. So as in, so she has. So you see the large x at the start. That says
Yeah.
xb. So she has that. She has the lowercase version of that. Then she has the algebraic x, and then she has the expected.
Okay, now there is a difference in here because a capital X is the gosh, I forgot.
The actual whole set.
The whole set.
Yes, the capital X is your random variable,
And the small x is
and the small x is the variable of the integration.
Which is x1, x2, x3, x4.
So is that
So-
continuous?
Yes, yes, of course. If it's discrete, you don't do the integral.
Yeah.
If it's discrete, you're summing it up.
Yeah.
So the capital X is your random variable. In this case, it's a continuous random variable.
To the no x.
So, but yeah, so little x.
Little x is the values that your capital X as a random variable can take in between those two limits.
A and B.
So that's why that becomes the function of the integral.
Sorry. So is this and that the same thing then? They're both random variable.
No, capital X is your random variable, and the little x
No,
is
this
a
is the big one. This is not a
She
little
uses
x.
a
She uses this big
capital
one.
algebraic
Two
x.
circles. He says that that's everything.
I-
Data in it.
don't know what she means by that then.
So that one is
I
her
think she's doing the same
set.
thing.
That is her whole set. There's this one.
And then that's
Yeah, that's what she does. She does M and the X.
The
and then
Venn
she does
diagram,
that. It's the
isn't
same
it?
thing she does.
Same thing.
He's just writing it on the board. That's the problem. I guess.
You see when you have the square with the 2 circles in it, and the space of all of that.
Oh yeah.
That's the big curly X.
set.
Ah, so that's your world basically.
Yeah, the big curly X.
how you understand.
Because the problem is, because she's writing it on the board, it's so hard. Rather than use sort of a large straight x and then the little x is a sort of algebraic x, because obviously she needs to save that for the world thing. The problem is I never have any idea which is a capital and which is a lowercase.
Yes.
Ooh. So basically, f capital X bracket little x is the density function. It's your probability density function, the PDF. Okay? So that's an example there. So what is the probability of this random variable taking values between 0 and 1?
2e minus 2x. So that is 1 on top, 0 below.
So probability
Yeah.
of, right, what am I writing now?
So you can use the integrations and everything. 1, 0 below 1 top.
0,
And then 1.
Okay, y, oh yeah, 1, okay. And then
2e minus 2x. dt or dx.
dx. Okay, so how do I do this integral?
You've got it by parts, isn't it? So,
Mm,
no.
no, I wouldn't do by parts because the 2 can be brought out front.
Yeah.
You do minus.
So you've got the 2 outside, e minus 2x.
Yeah, so I can do that 2 times integral 0 to 1 e to the minus 2x dx.
So that would be e to the minus 2x over minus.
See, this is what I get. So wouldn't it just be minus a half e to the minus 2x? The integral of that? Of 2.
No, because you're mixing up 2 rules now. You're mixing up x to the n
Right.
with e to the x, and that's 2 different rules.
Right, okay. Okay.
You can do the substitution, yes, you can do the substitution. So you can do a u substitution, u being equal to minus 2x. So then du dx will be minus 2. So your dx is equal to du over minus 2. So the whole integral now, 2 times integral e to the u du over minus 2, but what else? Because I introduced u now, and it's a definite integral,
So you've got to find the value.
I need to find a new limit. So, if x was 0, u will be, I'm here, x is 0,
0.
u is 0, and if x is 1, u is
Minus 2.
so 0 to minus 2. So I bring out the minus 2, minus 1, 2 over minus 2, integral 0 to minus 2, e to the u du. So it's minus e to the u integral is
Over.
minus 2 over 2 is just minus 1. So I've got minus e to the minus 2, take away e to the 0. What? Yes. Yes. They have to, because that's what the algebra tells us. Because look, the u is now become negative. So the limits kind of switched around. Yeah. But if it wasn't negative, it wouldn't be. So this is minus e to the minus 2 plus e to the 0. E to the 0 is 1. So it's minus 1 over e squared plus 1. Or I can write it as 1 minus 1 over e squared. And that's more or less 0.86 to 2 decimal places. Now, I could have done it otherwise, a slightly easier way. Okay, so integral 0 to 1 to e to the minus 2x dx. If I look at e to the minus 2x just as a function, if I needed to differentiate that, that would be e to the minus 2x times minus 2. I already have got the 2 in here, so all I need is a negative in here, but if I bring a negative in here, I need a negative out. And then the integral of this one is e to the minus 2x. The antiderivative of this one is e to the minus 2x. So I could have just said this is minus integral e to the minus 2x between 0 and 1.
So that's what I was trying to say. So you don't have to do the substitution bit. Right. Okay.
Because basically it's the antiderivative of the chain rule. But if you don't see that, go down the substitution route, because that gives you exactly the same answer. Look, this is what we got here, and that is minus e to the minus 2 minus e to the 0. That's exactly what we just calculated there. Okay, that was a probability question. Now, I don't know if you've talked about joint probability yet.
Yeah, last year. Briefly.
Yeah, we spoke about.
Just like
Yeah, lightly.
So you can come across double integrals when studying about joint or marginal probabilities. So double integrals are antiderivative of two variable functions. Okay? Now the notation is important here because dx inside means that you're integrating with the variable x first, so you ignore the y, and then once you've done the integration with respect to x, then you can bring in the integration with respect to y. So it's important, and you cannot just easily switch from here to there, because that's going to play around with the integrals as well. So just be aware of that. If it's given to you as dx dy, you cannot just switch dy dx. That's just not how it works in mathematics. It's a little bit more complicated than that. Okay. So this is the definition of a joint.
I don't think we did this this week. We definitely did not do this last week.
Okay. Do you mind if I just show you anyway?
We did CDF.
It's CDF, but not really.
Well, the joint is just another version of doing the same thing, but with two variables. So you've got the joint distribution function defined by this, and finding the joint CDF is just applying that formula for the specific function. Okay, so, oops, get my notation right, because the statistics notation is just, okay. In the corner down here, you always put the capitals, because those are your random variables, okay? And then in the bracket, you have got the small x and y, because those are the specific values that those random variables can take. Okay, so what we got here is, and now you need to be a little bit careful with the notation, because look, you've got a's, b's, and x and y goes in the limits. So the joint distribution function was xy over 96. Now I change that into a and b over 96. And then I need to do dA dB. Basically, now I'm going to do two integrals. The first integral will be the inside, and the second will be the outside. So the outside I'm not going to touch for now. So that's just going to stay minus infinity to y. And then I'm going to do the integral of the inside. Okay. So as far as I'm concerned, my variable is a. So I can treat b as a constant. So I can bring out b over 96 and integral minus infinity to x a dA. And then I have got the integral to dB. Okay, so what is this integral? So I'm just going to leave these ones alone for now. What is the integral of a dA? A squared over 2. What are the limits? Okay, x is at the top definitely. Now minus infinity. Does my x goes down to minus infinity? Is 0. So I can replace that with 0, which is quite a bit handier. Okay, so I can now calculate that, but not forgetting that the rest I can't really do anything with at the moment, except for what is the lower limit of y? Well, y is only allowed to change between 1 and 5, is 0 otherwise. So I can just replace that with 1 to y. And then, what's going on in here? The top limit is x, so that's x squared over 2 minus 0 squared over 2 dy. Oops, not y, sorry, b. So integral 1 over y. Well, that one's basically just 0. So what I've got now is x squared b over, what is 2 times 96?
2 times.
Come.
192. 2 times 96, 192.
180, yeah.
180 plus 6. 180 plus 12, 192. Okay, dB. So I'm integrating with respect to b, so x squared and 192 can be taken out. And what's the integral of b, dB?
Of b squared over
And the limits are again 1 to y. So x squared over 192 times y squared over 2 minus a half. Okay, so I can factor out the 2 at the bottom because that's in both of the fractions. 2 times 192 is 384. X squared, y squared minus 1. So that is the joint CDF of this joint PDF.
So that's the whole, wow.
And is this where we're going to try to start
Is
finding
this
like
like
the
the-
covariance and stuff?
Expected values and the rest of it.
Because it's 2 variables. So.
Yeah. So you're going to use this for calculating marginal expectation or sort of joint probabilities, joint distributions and the rest of it. These kind of things. Trust me, I only touched the surface with this one.
Thanks for that.
But what I wanted to show you is you should not be afraid of it because you already know the integration stuff. All happens is that just like with, remember what happened when you first come across with multivariate differentiation? Letters were all over the place, but now you know what they mean. You're doing the same thing but other way around. So as long as you know which variable you're integrating by, just treat the rest of them as constants and then bring them out. Bring them out of the way and then you can deal with the integration that way. It needs some practice. So definitely, but I'm sure you're going to have quite a few practice questions, as always. And any other questions?
So does this thing go down the step of the correlation, like going down for probability and out? Like the multivariate stuff?
Yes, this is the multivariate stuff.
Correlation where you correlate. So.
Yes, I'm not 100% sure how much Arena goes into correlation, how much detail she goes into correlations, because there is quite a limit to what can be covered. But yes, this
Arena speaks very quickly.
Okay, if you have got.
Have a Merry Christmas.
Happy Christmas and have
Good luck.
Thank you. That's going to be, yes, I'm going to need luck, that's for sure.